Well, as soon as class ends, I need to skedaddle and leave campus. So what that means is, unfortunately, is that the video won't be up tonight because my internet connection at home is too slow. So I'll have it uploaded in the morning. Of course, that only affects one person who's not here right now. So, okay. Are there any homework questions of any kind? 5.2.3. Wait, 5.2.3? Okay. Do I sense some resentment? Okay. So at each search direction is orthogonal to a previous search direction. Okay. So what you need to do is, as a starting point, I should try to show that RK transpose RK minus 1 is 0. And so you can use the fact that RK is equal to B minus AX K minus 1. And, oh yeah, so I need to check my numbering scheme here because it's different depending on, I think I change it from one subsection to another. Okay. Oh, yeah, it's the same index. All right. So, XK. Yeah. But XK is XK minus 1 plus alpha K RK minus 1. So as soon as you substitute this in here, that's going to introduce, you're going to get terms that you can simplify to RK minus 1. And the formula for alpha K, you need to, oh, wait. That's alpha, so that's alpha K minus 1 also. Okay. So you need to put the formula for alpha K minus 1 in there. And then just have a big old cancel factor. So it is not a very long proof. Okay. All right. Any other homework questions?
I have one.
Yeah. 5.2.5. Okay. Okay, so the Lanczos function.
So when you look up at the algorithm, we've got on the next to last line above the end,
yeah,
we have the E1. How exactly are we supposed to find that?
E1 is the first column of identity.
Okay.
So it's going to be a vector of the appropriate size, which would be k by k.
Okay.
Yeah, and the first component is 1.
For some crazy reason, I was thinking it had something to do with error. So
oh, okay. Oh, not this time. Well, so, it's right elsewhere in the book I have EK referring to error, so that's a problem. All right. Any other? Nope. Okay. All right. Let's see how much further I can fall behind. So returning to okay. Now, so to recap the end of last time, that if you have a matrix B, which has this structure that is block upper triangular, then the eigenvalues of B come from the eigenvalues of the two diagonal blocks. Right, so you can reduce a problem to finding eigenvalues of two smaller matrices. It doesn't matter what the sizes of these blocks are. So B11 is P by P, and B22 is Q by Q, where P and Q can be anything. So a consequence of this is that if a matrix is upper or lower triangular, then the diagonal entries are the eigenvalues. Okay. Now, another thing to keep in mind from last time if A and B are related by what is called a similarity transformation, then A and B have the same eigenvalues. So we already have a mechanism for transforming the eigenvalue problem, and we have an idea of what kind of problem we want to transform it into, where we have some sort of a triangularity going on. So it won't be until Wednesday when I talk about exactly how that triangularity is going to be achieved. It's not going to be easy. But using these things, I'm going to establish a matrix factorization. So we've seen matrix factorizations before, like we have LU decomposition for Gaussian elimination. We also saw Cholesky and LDLT. And we also saw the QR factorization for least squares problems. So now we're going to have yet another factorization for eigenvalue problems. So really we're looking for the eigenvalue revealing factorization of A. All right, so I'm just going to step through now. Okay, so let's suppose we have some eigenvalue, lambda, and some eigenvector x that goes with it. So certainly that is going to be the case. We're going to have for each, at least for every distinct eigenvalue that A has, we're going to have an eigenvector that goes with it. Now, if A is n by n, you are not necessarily going to find n distinct or linearly independent eigenvectors, but it has at least one. So let's suppose we have that here. And I'm going to also assume that eigenvector, because the eigenvector has to be non-zero, as the definition of an eigenvector, so I'm going to make it a unit vector. So it's 2 norms 1. Okay. Then, let's suppose that P be a householder reflection Now, one of the homework problems from Chapter 4 homework, which I still have to grade, I know, and I hope to do that soon. Well, I'm not looking forward to it, but I will try to get to it like this week. Is one of the problems there was, given 2 vectors, A and B, find a householder reflection that transforms A into B if they have the same length. So that's what we have here. We can make a householder reflection such that P times X is equal to E1, the first column of identity. This is why I had to assume that X is a unit vector, because whatever P transforms X into has to have the same magnitude, which E1 does. Okay. Now, what that means is PE1 is equal to X. Now, P is an orthogonal matrix, therefore it's invertible. I can multiply both sides of this. I get X is equal to P inverse E1. But what's the inverse of a householder reflection? No.
P transpose.
What?
P transpose.
Well, P transpose, but what is P transpose when it's a householder reflection? Yeah, P inverse is P transpose because it's orthogonal. But we can narrow it down further because P is also, what's the other property that it has? No, it's really 1 out of 10. What?
Upper triangle, lower triangle, SQD.
I'm just throwing stuff out randomly.
Hey, I'll get there. I'm doing better than the silent folk behind me. I ran out. Those are the only 3 that came to my head.
Yeah. Well, 2 of you are trying to cram PD knowledge in your head, so you're excused. But but the rest of you. What? Sorry, I couldn't hear.
Symmetric.
Yeah. Yes. Therefore, B inverse is not just P transpose, but P. Yes. It's its own inverse. So I have from this, I can say X is equal to P inverse E1, but that's the same as P E1. So I could put P on either side I want, something you definitely could not normally do. Okay. So now I'm going to use that. So I have P. Wait. Now I'm going to assume that things are not necessarily real. In other words, instead of working with transpose, I can have a Hermitian transpose. So recall that Hermitian transpose is a transpose and complex conjugate. So really, to be proper, I'm saying that P is, well, I'm going to give you a real complex lingo. So P is equal to this Hermitian transpose. Now, if this is a real matrix, I would call it symmetric. But when it's allowed to be complex, the proper term is Hermitian, so we use the H. And from it being orthogonal to what we said normally, when it's a real matrix. So if this is a real matrix, we'd have P transpose P as identity, and we would say it's orthogonal. But when it's allowed to be complex, we call it unitary. And say PHP is equal to identity. So symmetric and orthogonal and everything is real. Hermitian and unitary if they might be complex. But we have corresponding concepts. So when I get sloppy, I tend to use them interchangeably. But okay. Oh, and then I'm actually going to compute. So this matrix here, this is a similarity transformation of A. Because pH is P inverse. Now pH is also equal to P, but so this matrix right here is going to have the same eigenvalues as A. Now what I'm going to do is I'm going to multiply by E1. When I multiply a matrix by E1, what am I getting out of that matrix? Well, what part of the matrix is that giving me? What is E1? What about?
This is the first column.
Yeah, so therefore I'm getting what here? First column of this matrix. Okay. Now, using the fact that PE1 is equal to X, it's going to give me PHA. So PE1 is X. But X is an eigenvector. So AX is lambda X. And lambda is a constant, it's a number, so I can move it out to the front. pH is P, so it's lambda PX. But PX, by design, is equal to E1. So it simplifies all the way down to lambda E1. Now, at this point, this probably means exactly nothing until I write out in full what this means. Because if we look at the full matrix, the first column is lambda times E1. Well, E1 is a vector that is all zeros except the first component is a 1. So the first component of this is lambda. And then everything else in that first column is 0. So now, the new matrix, the transform matrix, PHAP, has, at least in the first column, much simpler structure. And then we don't really know what is in the rest of the matrix, so I'm just going to give everything names. So I'll call this as a matrix B. So this is n minus 1 by n minus 1. And then up here is something, again, we don't really care what it is. It's just some row vector, so I'm going to call it VH. So I'm doing a transpose here because I want a row vector, and vectors are column by default. Okay. Now, why does this matter? Because of what I wrote earlier, that when a matrix has a block upper triangular structure, the eigenvalues of the whole matrix come from the blocks. So that tells me the eigenvalues of A are equal to lambda union the eigenvalues of B. So in other words, I've taken the eigenvalue we know, lambda, and this is my way of like setting it aside. Like we found it, we're done with it, and now we can move on to a smaller matrix B to find the rest of the eigenvalues. Now, this process that I've shown you here to basically take out one eigenvalue and separate it out, and so that we can look at a smaller matrix to focus on the rest of them, that is called deflation. So it's when the eigenvalue problem decouples into two smaller problems, one of which presumably we've already solved because we're assuming we have this, and then this other problem that is a smaller problem, and we can go ahead and work on that. Because then what I can do is I can then find, because this matrix has at least one eigenvalue eigenvector pair. So I can find an eigenvector of it and perform deflation on B to pick off that eigenvalue. I can keep going. So what I've done here is I've started to transform A to reduce it to upper triangular form. So I just repeat the process on B, then that's going to divide it into a block structure like this. It gives me a slightly smaller matrix again, and I just keep going until I have nothing left. So the result of all this, now, if I were being completely rigorous, I would say I would carry out a proof by induction, and well, F that. So my non-rigorous way of saying by induction, I would say continuing this process, what I get is the original matrix A is being multiplied on left and right by a unitary matrix Q to get an upper triangular matrix T. So Q is equal to identity, and Q is a product of whatever householder reflections we needed to perform a deflation at every step of the way. Furthermore, the diagonal entries of T are holds the eigenvalues of A. So any square matrix we can carry this out with. We can reduce A to some upper triangular form that reveals what the eigenvalues are. And we can write it this way: A therefore has this decomposition, Q, T, Q Hermitian Transpose. And that is called the Schur decomposition. Yeah. Or to refer to a movie that I hope you're all aware of. At least it's not sure.
What?
At least it's not sure.
Yeah, I don't know.
Okay.
He might.
Okay. Idiocracy 2005. So, know it, love it. Okay. Anybody besides Lewis?
The movie Idiocracy?
Yes. Yeah.
No.
Okay. Well, Lisa. What?
I don't remember that.
Okay. Well, hopefully it's not your future. But the way the world is going, I'm beginning to wonder. Yeah. There's a strange comfort in thinking, well, I can only be around for so much longer.
We all
Yeah. In any given period of time, things can only go to crap so much. Okay.
Maybe the dinosaurs will come back and the rest of the world will be
Okay. Well, we could do worse. Okay. Now, in MATLAB, you could do QT is equal to Schur of A to get the Schur decomposition. Okay. Although I should mention, the way the Schur decomposition works is if A is real, now real matrix will generally have complex eigenvalues. But if you give the MATLAB function a matrix that's all real, it's going to return Q and T that are also all real. So you get a slightly different Schur decomposition where Q tilde is a real orthogonal matrix. So Q tilde transpose Q tilde as identity instead of Hermitian transpose. And T is block upper triangular. And all the diagonal blocks are 1 by 1 or 2 by 2. 1 by 1 for real eigenvalues, 2 by 2 for complex conjugate pairs of eigenvalues. Because if A is real, yes, it may have complex eigenvalues, but like polynomial roots, which eigenvalues are, they have to occur in complex conjugate pairs. So you would get these 2 by 2 blocks. That way, you're avoiding complex arithmetic. If you really want those complex eigenvalues, at least you're just picking them off from a 2 by 2. That's very easy to do. So this right here is called the real Schur form. Yeah. Yeah, because you want to be real sure that you don't perform complex arithmetic. Yes, I know. Boo. And the algorithm that I'll be describing over coming classes will is what it'll actually compute. Okay. Now, one thing I want to emphasize, though, is that even though this gives us the eigenvalues of A, for a general matrix A, it does not give us eigenvectors, unfortunately. So I need to talk a little bit about that. Okay. So the matrix Q from Schur decomposition has these columns. And these are called Schur vectors. So these are not eigenvectors. Except for the first one. You can say that Q1 is an eigenvector, but otherwise there's very little connection between the Schur vectors and the eigenvectors. However, what you can say is that if I take columns of Q starting first and stop at any point, so Q1, Q2, that's a comma, up to Qj, it is what's called an invariant subspace. Of A. So in other words, if I take all of these vectors and multiply them by A, then what I get is still a linear combination of these same vectors. Or put another way, A times Qj is Qj Tj, where Qj has the first j columns of Q, and Tj is just the first j rows and columns. It's that j by j upper left block of T. All right, so at least we can say this much. So So you could use this relationship to get eigenvectors from the first j columns of Q. In other words, you can reduce it to a smaller problem, but there's still some work to do.
I'm guessing a vector can't have the quality of being both Schur and an eigenvector, or because Q1 is an eigenvector, it's both?
It is both, yeah. But the thing is, right now I'm talking about the case of a general matrix, but now I need to but now I'm going to talk about a class of matrices for which the two Schur vectors and eigenvectors are the same. So if A is a normal matrix, and what I mean by a normal matrix is A commutes with its own Hermitian transpose, also known as its adjoint. Okay. Then the Schur decomposition takes on a simpler form. It's Q dQH D is a diagonal matrix. So in other words, the upper triangular matrix that we have in the general case now becomes diagonal. And we have AQJ is lambda JQJ. In other words, each QJ, each Schur vector is an eigenvector. Now, what are examples of normal matrices? See, 0.
Oh, yeah, I did.
Well, yes, 0 is a normal matrix. But, for example, suppose A is Hermitian. So it's equal to its own Hermitian transpose. Then both of these would reduce to A squared. So they're equal. Also, if it's skew Hermitian, so A Hermitian transpose is minus A. So these are the simplest examples I can give, or the simplest interesting examples I can give of normal matrices. It turns out that a Hermitian matrix has real eigenvalues, whereas a skew Hermitian matrix has eigenvalues that are purely imaginary, or 0. All right, so these are important categories of matrices for which the Schur decomposition actually does give us the eigenvectors. Like Hermitian matrices will certainly come up, for example, in for important PDEs. Okay. Now, questions to this point. All right. Now, so what I speak about this case is we can see that if the matrix is normal, it's possible to perform a similarity transformation of A that reduces A to not just triangular form, but diagonal form, which is nice from a storage point of view. So I want to talk more about reduction to diagonal form. Okay. Now, so a square matrix A is said to be diagonalizable if you can find an invertible matrix P such that if you carry out the similarity transformation, P inverse AP is some diagonal matrix D. All right, so in other words, if it's possible to perform a similarity transformation that reduces A to diagonal form, we say that A is diagonalizable. So what we've just done here is we've diagonalized A. And what I can do is I can multiply both sides on the left by P. So I have that relationship. And if I let P have these columns, and D is a diagonal matrix that has these diagonal entries, then if I look at AP equals PD column by column, I have APJ is equal to lambda JPJ. In other words, the lambdas are the eigenvalues, and the columns of P are the eigenvectors. All right, so anytime you can reduce a matrix to diagonal form, you get everything. Eigenvalues and eigenvectors both. Now, what I just had over here with normal matrices is a special case of that. So if A is normal, you have QHAQ is equal to D. So, in other words, the matrix P that we had before is now Q that is a unitary, or in the real case, orthogonal matrix. So the eigenvectors are orthonormal. Whereas in this case, with P being an invertible matrix, all we could say before is that the eigenvectors are at least linearly independent. But if A is normal, we can make a stronger statement and say they're they form an orthonormal set. And the term we use for that is A is diagonalizable, but more so it is, more specifically, it is unitarily diagonalizable. Because Q is unitary. We like that because then we don't have to go to any effort to get the inverse. Because it's just a Hermitian transpose. Okay. The problem is not every square matrix is diagonalizable. So certain very important categories of them are, but not all. Now, every matrix, diagonalizable or not, still has a Schur decomposition. So you can always reduce to triangular form. It's just that you can't always reduce to diagonal form. So non-normal matrices, if it's still diagonalizable, you have a choice. You have to choose between Schur vectors that are, they may not have a nice properties of being eigenvectors, but at least they're orthogonal. Or you can have eigenvectors, which are nice to have, very convenient, but they're not orthogonal. in the normal case, you have both. Now, okay, let's see. All right, so the interest of not giving away to assign, so I haven't fixed my problems. So, one thing we can say is, suppose we have a set of eigenvectors. K eigenvalues, K eigenvectors. So K eigenpairs. And all of the eigenvalues, let's assume they are distinct. So no two of them are equal to each other. So you can show by induction that all of the eigenvectors involved, x1, x2, up to xk, are linearly independent. That's actually one of the homework problems, and again, it's something I might choose to assign, so I'm not going to work out the proof now. It's actually relatively easy to show in the case of, well, actually, I think in the book, yes, in the book I do work it out in the case where you have just two eigenvalues of two eigenvectors of distinct eigenvalues, and then the exploration gets into, okay, now how do you generalize that to the case of more than two? That's where induction comes into play. So, if k is equal to n, then you have a times all of these eigenvectors, all n of them, is equal to these same eigenvectors times the diagonal matrix. So what happens in that case is all of these eigenvectors that are linearly independent, if you have a matrix that has n linearly independent columns, these are all things that are supposed to be taught in 326, and whatever they stick is never matter. They form an invertible matrix, which I'll call X, and I'll call this D, diagonal matrix of eigenvalues, and you get X inverse AX is equal to D. Therefore, it's diagonalizable in that case. So, so if a matrix has n linearly independent eigenvectors, it is diagonalizable. In fact, that's an if and only if thing. What I've just shown here is if all of the eigenvectors are, if all of the eigenvalues are distinct, then that is one easy way to tell that A is diagonalizable. Now, the other possibility is that one or more of these eigenvalues repeat. In other words, maybe, so in other words, at least one of these eigenvalues is a multiple root of a characteristic polynomial. In that case, it's uncertain. A might still be diagonalizable, it might not be. It just depends on the matrix. So I come up with examples where either one may happen. Okay. now, what?
Did you not hear that?
People were saying somebody's getting murdered.
I said, I think someone just died.
I know.
I mean, there's like screeching.
Murder.
I heard it.
I did too.
Well, everything seems normal out there, but
It's like I got stuff in the double vents. Duck work.
what?
Sound like somebody got stuff in the duck work. Sound horrible.
Well,
My money's on Dr. Harris.
okay. Well, a couple years ago, I had in my outer room there. I had birds getting stuck. Like they came down
Oh, I
through the.
remember when there was a bird in your office that I had to catch and take it outside.
Yeah. And unfortunately, there were a few birds who died. One got stuck in there over the weekend. But.
That smelled wonderful.
Yeah, because I was in there minding my own business, and all of a sudden there was this. I was like,
Yeah.
"Come here." Then I caught it in the shoebox. I don't know where I got the box from. Anyway, your office, because you got boxes.
Yeah.
That's what
Anything can happen, I guess. Okay. Let's see. Now, how much detail I want to go into here? Okay, I have 36 minutes. Okay. Okay, yeah, so I do need to talk about, I mentioned a repeated eigenvalue is a repeated root of a characteristic polynomial. So in that case, the eigenvalue has a certain multiplicity to it. But when it comes to eigenvalues and eigenvectors and characteristic polynomials, we actually have more than one notion of multiplicity to talk about. And that helps us get a handle on whether a matrix is diagonalizable or not. And if it is not diagonalizable, do we have some other decomposition that is, if not diagonal, it's close to diagonal. So, check my notation here. Oh, okay. I didn't bother giving these things names. So any eigenvalue lambda has.
Is it an eigenvalue or any eigenvalue?
Well, I'll go either one. So why or no, why, I don't care. But it has an algebraic multiplicity, which I'll call M. And that is the number of times lambda appears in the factorization of a characteristic polynomial. So in other words, if I wrote out the characteristic polynomial in factored form, and a whole bunch of linear factors, some of which may repeat. So I have like lambda minus 2, lambda minus 2, lambda minus 2. So lambda minus 2 cubed, in other words. Then the algebraic multiplicity of the eigenvalue 2 would be equal to 3. So, so here we're just talking about multiplicity of polynomial roots. We're not thinking really about eigenvalues at this point. Okay, so that's the algebraic multiplicity. And then we have the geometric multiplicity. I'll call G. And that is equal to the number of linearly independent eigenvectors that this eigenvalue has. So an eigenvalue will always have at least one linearly independent eigenvector. It might have more than one. Okay. So how do these... Quite a sniff fest going on here. Well, not just you. We're doing a symphony there. All right. So a relationship between algebraic and geometric multiplicity is the geometric multiplicity is always less than or equal to the algebraic, and the geometric is also at least one. So every eigenvalue is going to have at least one linearly independent eigenvector, but that could never exceed the algebraic multiplicity. Also, if it turns out that geometric multiplicity is strictly less than m, then we say that lambda is defective. In other words, it does not have as many linearly independent eigenvectors as it could have. So it's not playing with a full deck. So now from this I can make a statement that the matrix A is diagonalizable if and only if A has no defective eigenvalues. Okay. So in other words, it took a lot of Walmart receipts and got some working ones. It's Monday. Okay. Now, so for instance, any normal matrix, which we already know is diagonalizable, does not have any defective eigenvalues because all the eigenvectors are not just linearly independent, they're orthonormal. Okay. So what happens in the case where you have at least some defective eigenvalues? Well, in that case, we have another decomposition. So we actually have 3 decompositions in total of interest for related to eigenvalues. So we have a Schur decomposition, and that exists for any square matrix. We also have this decomposition. This is called, I didn't give a name earlier, it's called the spectral decomposition. However, it only exists if A is diagonalizable. And at least this one gives us the eigenvectors. So the columns of P are the eigenvectors. In both cases, the diagonal entries of T or D are the eigenvalues. Okay, and then the last decomposition XJX inverse, that is called the Jordan canonical form. And And this exists for any square matrix. All square matrices have a Jordan form. Now, X is some invertible matrix. Now, what about this J? What form does it have? It may not be diagonal. It is block diagonal. I want to check my notation here. Okay. Yeah. And each one of these blocks has this kind of structure, where we have some eigenvalue along the diagonal. And notice I made all of these entries the same. So same lambda all the way down the diagonal. And then you have ones above, the super diagonal, everything else 0. So not quite diagonal, but pretty close. So this is called a Jordan block. Now, the number of blocks that you have, so in other words, P, so this is equal to the number of linearly independent eigenvectors that A has in total. So what that means is, if you had n blocks, well, n's all you have room for, so each one of these would be 1 by 1. Then your Jordan form would reduce to a spectral decomposition, because you'd have a full set of linearly independent eigenvectors. Because each one of these Jordan blocks has only one linearly independent eigenvector. So if you have any block like this that's non-trivial, that actually has these ones, in other words, it's larger than a 1 by 1, that means the eigenvalue lambda is defective. Okay. All right. So now the thing is, I have more than one Jordan block associated with a particular eigenvalue. So in fact, I could describe both multiplicities of an eigenvalue in terms of its Jordan blocks. So, all right, so where I define these multiplicities, I'll fill in that relationship. So the geometric multiplicity is equal to the number of Jordan blocks for a given eigenvalue lambda, regardless of the sizes of those blocks. And then the algebraic multiplicity M, that you get that number by adding up the sizes of all of those Jordan blocks. Or that have that particular eigenvalue on the diagonal. Okay. So as an example, so suppose I have eigenvalue of 2 with a 3 by 3 Jordan block, and then I have an eigenvalue 3 with a 2 by 2 Jordan block, so there's only one on the superdiagonal. And then I have 2 appear again, in a 1-by-1 block. So what I can say in that case is, for lambda equals 2, the geometric multiplicity is 2, because I have 2 Jordan blocks that have 2 on their diagonals. But the algebraic multiplicity of the eigenvalue 2 is 4, because I have a 3-by-3 and a 1-by-1, so I just add those two sizes together. And then for the other eigenvalue 3, the geometric multiplicity is 1, because there's only one Jordan block that has 3 in it. And the algebraic multiplicity is 2, because that one Jordan block is 2-by-2.
Will you explain why M was 4 again, please?
Oh, if you take the 2 Jordan blocks that feature 2, add up the sizes. Okay. So, now this is a 6-by-6 matrix. Your algebraic multiplicities, therefore, must add up to 6. But your geometric multiplicities, not necessarily. It's going to be, it's less than or equal to. So this matrix is very defective. Because you could have as many as 6-by-6 matrix, you could have up to 6 linearly independent eigenvectors. This one only has 3. So both. What?
Where 3? Because 1, 2.
Yeah.
2, 3. Yeah.
Yeah. So there's 3 linearly independent eigenvectors in total. So both distinct eigenvalues that you have, 2 and 3, they're both defective. Okay. So in the case where you have 1-by-1 Jordan blocks, then the corresponding columns of X, those are eigenvectors. Whereas if you don't have a full set of eigenvectors, what you have instead are called generalized eigenvectors. And I actually have one of the problems, again, I may or may not assign it, that get into what the generalized eigenvectors are. So now that we have these 3 decompositions, I want to talk about what do we do from a computational standpoint. Since we're trying to compute eigenvalues and eigenvectors in the first place. Okay. Now, so of these 3 decompositions, which one is more practical from a computational standpoint? Keeping in mind that it's a computer that's doing the work. It's carrying out all the arithmetic. So I'll talk about these 3 in turn. The best one is a Schur decomposition. And the reason why is it uses orthogonal transformations. And those are perfectly conditioned. The condition number of an orthogonal or unitary matrix is 1, which is the smallest it can be. So from a numerical standpoint, it's very stable. Now, we don't get the eigenvectors out of it unless A happens to be normal. So that's one unfortunate thing. Yeah, but from a computer arithmetic standpoint, in terms of round-off error, conditioning, etc., Schur is best. The spectral decomposition, I'd say that's so-so. Because once you have the eigenvalues from a Schur decomposition, if I try and compute this, I can get from this to this. I won't have time to cover it in this class, unfortunately. Well, it's this or saying something about machine learning, take your pick. The algorithm is kind of a pain to carry out. But from numerical stability standpoint, it can be problematic if the eigenvalues are almost linearly dependent. So if eigenvalue, if you, because at least with a normal matrix, your eigenvectors, oh, sorry, not eigenvalues, eigenvectors, dang it, are almost linearly dependent. Can't talk about numbers. Dependent. Yeah. So in other words, if two eigenvectors are nearly parallel to one another, or more generally, if a certain eigenvector is almost a linear combination of other ones, then you might have a problem computing them accurately.
I'm going to ask a silly question.
Okay.
Define something that's almost parallel.
Well,
give me two slopes that would be almost parallel.
like something like that in 2D. They're pointing almost in the same direction, but not quite. So technically, those vectors are linearly independent. But since they're pointing in almost the same direction, like, and here it's kind of exaggerated so you can see it. But what if that difference in direction is no smaller than like round-off error? Then you really have no idea. And that takes me to the other decomposition that we have. So what about computing the Jordan form? As far as the practicality of computing that, I can summarize in one word. Don't do it ever. I'll give an explanation.
No exploration.
No coding explorations for this, right? Yeah, that'd be a pretty horrendous problem to give.
Actually, we would just answer it with don't.
Yeah. Well, okay. I guess that'd be a comment or something. Or put on an error message. Why are you computing this, you idiot?
You said not to.
Code should work that way. It should yell at you more. Well, I mean, I guess code yells at us anyway, but yeah. Okay. So I'm going to give an example as to why it is actually computing is using computer arithmetic is a non-starter. So let's suppose you have these matrices. So two matrices are almost identical. So the only difference between them is the 2-2 entry is perturbed by a very slight amount, by 10 to the minus 9. Now, this matrix here is diagonalizable. How do I know that just by looking? What are the eigenvalues? Yes, Both matrices are upper triangular, so you can read the eigenvalues off a diagonal. So what kind of matrix do we know is diagonalizable? If the eigenvalues are what?
Invertible.
Distinct. Yeah, so here we have two eigenvalues, 10 and 10.0001. So anytime you have a matrix with distinct eigenvalues, no matter how close together they are, that's still a diagonalizable matrix. And so I could find an x so that x inverse times a1 times x is diagonal. Okay. This matrix is not. It's not diagonalizable. So we have one distinct eigenvalue, 10. It has a algebraic multiplicity of 2. It has a geometric multiplicity of only 1. So that eigenvalue is defective. So what would be the Jordan form for these two matrices? Well, the second matrix actually already is in Jordan canonical form. So the J matrix is itself. We have that 1 sitting there. Whereas A1 has this Jordan form. It's a diagonal matrix because the matrix is diagonalizable. So when a matrix is diagonalizable, the Jordan form is that diagonal matrix that it can be transformed into. So now, let's compare these two matrices. They are, so it's almost like from, it's almost like a thing from like Sesame Street Electric Company, or I know it's a My Generation thing. Like, yeah, 3 of these things are the same and one's different.
Yeah.
Yeah.
They also had that in Highlights magazine.
Oh, okay. They still have those?
I don't know that they still have them.
Like in every doctor's office in America?
They
Like
had
the
them.
box, take the box of the buddies.
Okay, yeah.
Swap box.
All right. So, where do we see a
Where you're sick all the time now.
where do we see a significant disparity? Yeah. So notice the two original matrices are extremely close to each other. So A1 minus A2, if I were to, let's say, take the infinity norm of that, well, all the entries are the same except for the 2, 2 entry. So it's 10 to the minus 9. So A1 minus A2 is extremely small. But if I do the same with J1, J2, these also, like if I say take the infinity norm is the largest, oh, actually, yeah, so maximum row sum. Okay, it's 1. So, a small change in the matrix results into a relatively large change in a Jordan form. So this is the very definition of an ill-conditioned problem, that a small change in the input data results in a relatively large change in the output data. So when it comes to ill-conditioned problems, computing a Jordan form is about as ill-conditioned as they come. Another way of putting it is that the Jordan form is not a continuous function of the entries of A. So, as another way of saying, tiny change in A could result in sharp jump change in the Jordan form. And that's a kiss of death for numerical computation. There's just no way. Because, well, in other words, what happens is, if you have a situation like this, these kind of eigenvalues that are so close together, how do you know if they're meant to be two distinct eigenvalues that just happen to be really close together, or if they are a repeated eigenvalue, and whatever gap you have between them, like a 10 and minus 9 gap here, is just round-off error? You don't know. And yet, which one of those cases it is alters the whole structure of the Jordan form. And since you can't really tell those cases apart when you're talking about when you take round-off error into account, what can you do? How do you really decide what is a correct Jordan form? Whereas if a Schur decomposition, or even a spectral one, a small change in the input should result in a commensurately small change in the decomposition. So those are okay. Now, maybe less so for spectral, because again, you might have nearly linearly dependent eigenvectors, but still, at least it's within the realm of possibility. And maybe just some pathological cases go bad. But Jordan form, you just throw up your hands. Forget it. Which is unfortunate because it's such a useful decomposition to have. So fortunately, there's still, like I said, there's still very important classes of matrices that are nicely behaved, like normal matrices, symmetric matrices, etc., for which Schur decomposition reveals not just the eigenvalues but eigenvectors. So we're getting by all right without being able to compute the Jordan form. Okay, so almost out of time. Okay, I will say a little bit next time just about perturbation theory, but then what I really want to get into on Wednesday is start getting into algorithms for actually computing eigenvalue, eigenvector pairs, and I'll also figure out which problems I'm going to torture you guys with.
It's your job.
Yes, literally. So,
And it's our job.
okay, so all right, so we'll have fun with that later. All right, so we can all get out of here a little bit early, so that compensates for starting a little bit late.